Hi, good morning, everyone. Good morning. Are there questions for homework? I think we are done with thermodynamics theory. And I told we are starting a new topic today. Correct, if I'm not mistaken. So tell me, right. What are the questions for homework? 14? Right, question 14. Natural gas produced from landfill consists of a mixture of methane and carbon dioxide at a temperature of 20 degrees Celsius and a pressure of 1.01 to 5 pascals. The volume occupied by 1 mole of carbon dioxide is given. Show that the number of molecules in 1 mole of carbon dioxide is this much. We have to find the number of molecules. So we can use PV equals NKT. PV equals NKT. Number of molecules N equals PV over KT. P is the pressure. Pressure is given 1.01 10 to the power 5. Volume is 0.0241. Over K is the Boltzmann constant, which is 1.38 into 10 to the power minus 23. Correct? Into T is the thermodynamic temperature, 20 degrees Celsius is 273 plus 20 is 293 Kelvin. So the number of molecules will be 6.02, or to two significant figures, 6.0 into 10 to the power 23, the number of molecules in 1 mole of carbon dioxide at the given pressure. Okay. Right. In a sample of natural gas, the RMS velocity, the root mean square velocity of carbon dioxide molecules, is 60.5% of the RMS velocity of the methane molecules. RMS velocity is the square root of mean square value, mean square speed. Reduce the ratio of mass of carbon dioxide molecule over mass of methane molecule. Okay. In a sample of natural gas, the RMS velocity of carbon dioxide molecules is 60.5% RMS velocity of the RMS velocity of the methane molecules. Now,
So what's the full form of RMS?
root mean square velocity. RMS is root mean square. Okay. Now, it's a mixture of methane and carbon dioxide. So that means both methane and carbon dioxide are at the same temperature. Agree? So since both carbon dioxide and methane are at the same temperature, their mean kinetic energy will be the same. Yes or no? Kinetic energy depends on the temperature. Ek equals 3 over 2 kg. Correct? So if both are at the same temperature, both will be having the same mean kinetic energy. So I'm going to begin with this. Mean kinetic energy of carbon dioxide is the same as the mean kinetic energy of methane. Okay. So mean kinetic energy of carbon dioxide, I can write it half into m into, where m is, I will take the mass of carbon dioxide, I will take it as mc into c square of carbon dioxide, I will take it as c square of c, or I will take it as cc square. That is equal to half mean kinetic energy of methane will be m methane into c methane square. Mean kinetic energy of carbon dioxide molecules is equal to mean kinetic energy of methane molecules because they are at the same temperature. So I equate the kinetic energy. Then the halves on either side should cancel off. What are we told to find? Mass of carbon dioxide molecule over mass of methane molecule. Mass of carbon dioxide over mass of methane. Mass of carbon dioxide over mass of methane will be C m square over cc square. Okay. So now they have told already that 60.5% story. What is that? The RMS velocity of the carbon dioxide molecule is 60.5% the RMS velocity of the methane molecule. Now I can see m square. If I take the square root of this, okay. If I take the, actually this square should come in my notation. The square should come in mean square speed. Now, the square root of this is going to be the CRMS. So what I'll do is, now this is the equation. If I take the root on either side, okay, that is going to be mass of carbon dioxide over mass of methane square root is going to be CRMS of methane over CRMS of carbon dioxide. So that is what they have told. RMS velocity of carbon dioxide is 60.5% of the RMS values of methane. So what have they told is CRMS of carbon dioxide over CRMS of methane. This is 0.605, 60.5%. RMS velocity of carbon dioxide over RMS value of methane is 60.5%, which is 0.605. Am I right? So what I have made here is the reciprocal of it, CRMSM over CRMSC, which is supposed to be 1 over 0.605. Okay, that is square root of MC over MM. We have to find MC over MM, mass of carbon dioxide over mass of methane. That is 1 over 0.605 needs to be squared. (2.732). I'll take it as 2.73. Now it's a mixture of both. So both are in contact with each other. So both are having the same temperature, yes or no? So kinetic energy depends only on the temperature. So if they have the same temperature, that means they have the same kinetic energy. Correct. That's why they have different speed, so that their kinetic energies are the same. If the temperature is the same, kinetic energy will be the same. The theory is Ek equals 3/2 kT. K is a constant. 3/2 is a constant. So Ek purely depends on the temperature. Okay, done. What's next? Question 15. According to the Football Association rules, the football used in a professional match should have a circumference of between 68 centimeters and 70 centimeters. The pressure of the air in the football must be between 60 kilopascals and 110 kilopascals. Above atmospheric pressure, a football was inflated with air at a temperature 16 degrees Celsius. When inflated, the circumference of the football was 6. Which table is that? That one. Then this one. Can you please move to that? This one. A football was inflated with air at a temperature of 16 degrees Celsius. When inflated, the circumference of the football was 68.5 centimeters, and it contained 2.5 into 2423 molecules of air. Deduce whether this football met the FA rules. Atmospheric pressure is 105 kilopascals. The football was inflated with air at a temperature of 16 degrees Celsius. When inflated, the circumference of the football was 68.5 centimeters. And it contained this much of molecules. Deduce whether this football met the FA rules. That's an easy question, even though it's a 6 marker. Atmospheric pressure is 105 kilopascal. Right. So guys, we can find the volume of the football. Football is a sphere. Volume of a sphere is given by the equation 4/3 pi r cube. Correct? Which is 4/3 pi. The circumference is 68.5. We don't know the radius, so I can find the circumference is 68.5 means circumference equals 2 pi r. From there, I can find the radius. 68.5 centimeters equals 2 pi r. That gives you the radius, which is 68.5 divided by 2 pi. 10.902. I'll take it as 10.90 centimeters is the radius, which is in meters 0.109 meters. That is the radius. So if I use that here, 0.109 cube, that gives you the volume of the ball, which is 5.4246 into 10 to the power minus 3 cubic meters. This is the volume of the ball. So then using PV equals, we know the number of molecules. So I can use PV equals NKT to find the pressure. So P equals NKT over V N is the number of molecules, which is 2.5 into 10 to the power 23. K is 1.38 into 10 to the power minus 23. Temperature is 16 degrees Celsius, which is 273 plus 16 is 289 in Kelvin. Over the volume is what we just found. The volume is 5.4246 into 10 to the power minus 3. So that's going to be 183,801.6 pascals. So what is the requirement, which is 183.8 kilopascals. This is the pressure of the ball. Okay, pressure of air in the ball. So what are they saying? The rule is the pressure of the football must be 60 kilopascals, between 60 and 100 kilopascals above the atmospheric pressure. So the atmospheric pressure is 105 means. So the real limit is 105 plus 60 to 105 plus 110. 105 plus 60 is 165 to 105 plus 110 is 250. This is the absolute pressure limit. So 183.8 is the value that we are getting, which is fall in between. So that means fine. Correct? 183.8, right? What did you get? Huh? Not 183.8? Okay. Okay, anyone else getting a different pressure? Anyone getting 184 or anything different from that? Okay, so now what are they saying? The requirement is the pressure of the air in the football must be between 60 to 110 kilopascals above the atmospheric pressure. So the atmospheric pressure is 105 kilopascals. So that means 105 plus 60 is 165. 105 plus 110 is 215. So that means the pressure of air in the ball has to be within these two values. That is the requirement. Am I right? Where now we have got it as 184. That means it's fine between the two. Correct? So write the statement. Yes. It meets the FA rules. Check your working again. Right. The next one. The pressure inside a football decreases as the temperature of the air inside falls. Temperature is falling, pressure is decreasing. The volume of the ball remains constant. Explain why in terms of the motion of molecules. It's an easy answer, but it's a 6 marker. You have to write a in detail answer. Now, when the temperature decreases, according to EK equals 3/2 kT. If the temperature is decreasing, the mean kinetic energy of the molecules is decreasing. Correct. Mean kinetic energy of the molecules is decreasing means the speed, the mean speed or the speed of the molecules will decrease. Yes. So the speed of the molecules is decreasing means inside this ball, the molecules will be colliding the wall less frequently. Speed is reducing. Correct. So they collide with the walls less frequently means the rate of change of momentum of these molecules will be less. So which means the force exerted on the walls will be less. Pressure is the force per unit area. Force is less means the pressure is less. Correct? Right. When the temperature decreases, mean kinetic energy of the molecules will decrease. Mean kinetic energy of the molecules will decrease. Full stop. So the
Good, sir. Could you please start repeating, sir? Because I thought you were explaining it again.
when the temperature decreases, the mean kinetic energy of the molecules will decrease. Okay. Full stop. So the mean speed of the molecules will decrease. The mean speed of the molecules will decrease. Full stop. Molecules will collide with the walls. Molecules will collide with the walls less frequently. Less frequently. Full stop.
So if you write this formula and everything, will you get like extra
No.
marks?
No, even if you write, okay, but not a mass. Full stop. So the rate of change of molecules will decrease. Rate of change of molecules will decrease. Rate of change of momentum of the molecules. What did I tell?
So using molecules, I was real confused.
Rate of change of momentum of the molecules. Rate of change of momentum of the molecules will decrease. The force exerted on the walls will decrease. Force exerted on the walls will decrease. Full stop. Pressure is the force exerted per unit area. Pressure is the force exerted per unit area. So the pressure will decrease.
So can you say the last part again?
The pressure is the force acting per unit area. So the pressure will decrease. Okay. Yes. Can you read the answer again and see if there's anything missing?
We have to explain why the volume will be constant.
No, but that is already told, no? By the 18th one, a cyclist completes in a bicycle. 17th we have done. 16th, did I ask you to? 18th and 19th I have marked. 18th, 19th, 20th I have marked. 18th, a cyclist competes in a bicycle race. Before the race, a bicycle tire contains air at pressure, temperature 22 degrees Celsius and pressure 5.5 to 10 to the power 5. By the end of the race, the pressure of the air in the tire has risen to 5.6 to 10 to the power 5. Calculate the temperature of the air in the tire at the end of the race. Okay. Now, PV equals nRT. Correct. So the volume of the tire will remain the same. Number of moles or the number of molecules in the tire will remain the same. R is anyway a constant. So which is basically V in R constant means P is directly proportional to T. Am I right? So which means I can consider that P over T is a constant in either cases. So I can tell you P1 over T1 equals P2 over T2. P over T ratio is a constant. So at the beginning, what is the pressure? 5.52 into 10 to the power 5. And the temperature is what?
Recording in progress.
Okay, so P1 over T1 equals P2 over T2.
Sir, you're not.
What? What?
Yeah, even screen share.
Okay. Patience. So initial pressure over initial temperature is equal to the final pressure over final temperature. From that, get the T2 subjected. That will be $299.3 Kelvin. So if you don't like Kelvin, you can minus 273 and get the Celsius temperature. Huh? You want to keep it to 199 Kelvin. Okay, happy? Right. Huh? Sorry? The universal gas comes 8.314. Okay. You don't like this equation. You can still take this one. PV equals NKT. Same thing. V is a constant. The number of molecules N is a constant. K is a constant. So which means P over T is a constant. T is proportional to T. Okay. Right, the next one. During the race, a small amount of air escapes from the tire. Explain how the values of temperature calculated in one would be affected if allowance were made for this escape there. During the race, a small amount of air escaped from the tire. Explain how the value of the temperature calculated in one would be affected. Okay, PV equals NKT. Okay. V is anyway a constant, K is constant. They're asking if the number of molecules is going to decrease, what will happen to the T? If the volume, number of, they are saying explain, during the race, a small amount of air escaped from the tire. That means the number of molecules in is going to decrease. No, the volume is constant. The tire volume of the tire is constant. The shape of the tire is not going to change.
Increases, right, sir?
Okay, so if the N is not going to decrease, to compensate for that, T will have to increase. Correct? So right. To marker, you can show the equation. Write the equation and write. Temperature will increase. The next one is very similar to the previous question that we answered. Explain why pressure exerted by the air in the tire increases as the temperature of the air increases. The previous question that we answered is when the temperature decreases, how the pressure decreases, right? The previous question for a 6 marker we answered. Now for a 4 marker they have asked how when the temperature is increasing. Now explain why the pressure exerted by the air in the tire increases as the temperature of the air increases. So your answer has to be when the temperature increases, the mean kinetic energy of the molecule will increase. So the speed of the molecules will increase. So the molecules will collide with the walls more frequently. So that means the rate of change of momentum is high, force is high, pressure is high. Okay, so I'm not going to give that answer. You can just look at the previous one and answer this. What's next?
The earlier page. Okay.
19th. The coffee is made with hot water and milk. The water used to make the coffee is heated to its boiling point. Describe the changes in internal energy of the water while it is boiling. While it is boiling, what will happen to its internal energy? Yeah, we didn't do it here. Correct. So guys, while it is boiling, will the temperature increase? Tell me, boiling happens at what temperature? 100
100
degrees
degrees
Celsius.
Celsius. It doesn't increase until it's complete, the boiling.
Yeah. Until the boiling process completes, the temperature will remain at 100 degrees Celsius. Now we know that the mean kinetic energy of the molecules will depend on the temperature. Correct? So if the temperature is going to remain constant, the mean kinetic energy of the molecules will not change. Correct? So they're asking, describe the changes in the internal energy of the water while it's boiling. Because the temperature is remaining constant, the mean kinetic energy of the molecules will remain constant, but whatever the energy that you are supplying will be used to, will be stored as potential energy. Okay, so internal energy, I told you it has two components, kinetic and potential energy. Okay, so kinetic energy is remaining constant, but the potential energy that will increase. So right, it's a true marker. So the internal energy will increase. Temperature is constant. Right? Mean kinetic energy of the molecules will remain unchanged.
So please repeat, sir. Sorry.
Sorry?
Please, if you don't mind, repeat it, sir.
Kinetic energy of the mean kinetic energy of the molecules will remain unchanged or will remain constant. Yeah. Not a must. Mean kinetic energy of the molecules will remain constant. The potential energy of the molecules will increase. So the internal energy will increase. Increase. So the internal energy. Right. The cup contains 45 grams of coffee at a temperature of 73.5 degrees Celsius. Milk at a temperature of 62 degrees Celsius is added to the coffee. The temperature of the mixture immediately after adding the milk is 65.5 degrees Celsius. Calculate the mass of the milk that was added to the coffee. Specific heat capacity of coffee is given, specific heat capacity of milk is given. Okay, so now coffee is at a temperature of 73.5, milk is at a temperature of 62, means when you mix it, coffee is going to release energy, milk is going to absorb energy. So energy released by coffee is equal to energy absorbed by milk. Correct? So energy released by the coffee will be mc delta theta, where mass of coffee is 45 grams, which is 0.045 kilograms. And C, specific heat capacity of coffee is 4,200. Delta theta is 73.5 minus 65.5. 73.5 minus 65.5. How much is that? 8. And the energy absorbed by the milk will be mc delta theta. M is what we want. Specific heat capacity of milk is 3,900. delta theta for milk is temperature is increasing from 62 to 65.5, 3.5 degrees Celsius. Correct? So the M is going to be 0.1107, which is 0.1108 kilograms, 110.8 grams. Or 111 grams. Okay. Are you doing unit 4 papers at home? Yes, right?
So
At
can go
least-
back to one second.
At least one paper a week. You're doing, no? Yes, right? Correct, right?
Done.
What is the barrier? What is the meso? What is the quark composition of proton? 2 up and 1 down. Capital. What is the outer name? Okay, I'll check. Thank you.
I'll take the A1.
Yeah, remove that. Don't bring it. Go and throw that. Seriously.
Thank you.
Right. There's the next one. 20th. Tires for racing bicycles are often filled with nitrogen gas rather than air. Should you do this? Looks like the same thing again. Have you done this question? Yes. Tires for racing bicycles are often filled with nitrogen gas rather than air. Yes. The tires are inflated using small cylinders filled with nitrogen gas at high pressure. The photograph shows such a cylinder. The tires are inflated using small cylinders filled with nitrogen gas at high pressure. The photograph shows such a cylinder which is filled with nitrogen gas. The cylinder has a volume of given, contains this much of molecules. Temperature of the nitrogen is given. Show that the pressure exerted by the nitrogen gas in the cylinder is about this much. PV equals NKT. P equals NKT over V. N is number of molecules, 6.85 into 10 to the power 22. K is 1.38 into 10 to the power minus 23. Temperature is 22, which is 295 Kelvin. Volume is 7.25 into 10 to the power minus 5. Three point 85. 3.85 into 10 to the power 6 pascals. Are you getting this answer? Nitrogen gas at temperature of 22 degrees Celsius is used to fill a bicycle tire of volume 1.17 into 10 minus 3 cubic meters. Show that 3 gas cylinders contain the amount of nitrogen gas needed to fill the tire to a pressure of 6.55 into 10 to the power 5 pascals. So I want to find how much gas molecules are required to fill a tire, which is N equals PV over KT. So pressure is 6.55 into 10 to the power 5. Volume of the tire is 1.17 into 10 to the power minus 3. Divided by K is 1.38 10 to the power minus 23. T is 295. This is the number of molecules required to fill the tire. That's going to be 1.882 into 10 to the power 23. These are the number of molecules required to fill the tire. So then one cylinder has how many molecules? 6.85 into 10 to the power 22 molecules. So number of cylinders required will be 1.882 into 10 to the power 23 divided by the number of molecules in one cylinder is 6.85 into 10 to the power 22. Which is 2.75 cylinders. That is about 3 cylinders. Okay. Find the number of molecules required in total. Divided by the number of molecules in one cylinder. Right. The next one. The next part is in practice, more than 3 cylinders of nitrogen gas may be needed to fill the tire to a pressure of 6.55 into 10 to the power 5 pascals. Suggest a reason why. One marker. Now we calculated we need about roughly 3 cylinders. Why? One is, yes, now you are using the cylinder and inflating the tire. While you are inflating, there can be some molecules which is escaping into the air. That is one reason. Another reason is, now when you, listen to this part, use a cylinder and when you inflate a tire, are you going to take all the molecules that is in the cylinder? Can you do that? Can you suck it up? So what happens is, The cylinder is storing air at a high pressure. Okay, the gas at a high pressure. So when the cylinder is releasing the air molecules into the tire, now let's say this is a cylinder. Okay, now you have a tire here. Now when you connect these two, what happens is when the gas molecules are entering into this, now these two are now open. Eventually they come to a equilibrium pressure. The pressure of the gas tire is increasing, and the pressure of the gas cylinder is decreasing. Okay, so there comes a point the pressure in this
Where
is
they both are equal.
equal. So at that point, even if you keep the valve open, there's no gas molecules going to go from one to the other because the pressure is the same. Okay, why the gas was flowing from the cylinder to the tires? Because it was moving from a higher pressure to the lower pressure. So once they reach the same pressure, okay, there won't be gas flowing from the cylinder to the tire. So which means you can't suck up the entire gas molecules in this cylinder. Even after you inflate it, there will be some gas molecules remaining in the pressure cylinder. You can't make it a vacuum anyway. You get it? Can't make it
So
a
if
vacuum.
that were to happen, the cylinder would shrink, right, and crush.
Yeah, that is another thing. If that is the case, outside the atmospheric pressure is there, and inside the pressure is going to be zero. If the material is not so strong, it can even change shape. The cylinder can change. Okay, it can shrink. Fine. So I gave you two reasons. One is you can say the air particles can escape into the air, and more than that, what I think is the reason is you can't completely take all the molecules out of the cylinder. There will be some molecules remaining. There will be molecules remaining in the cylinder as the pressure reduces. Right? All the molecules in the cylinder will not be used. All the molecules in the cylinder will not be used to inflate the tire. Some air will remain in the cylinder. Yeah, it's a one marker, that is enough. We can't give a detailed answer in that case.
So could you repeat that, please?
Not all the molecules in the cylinder will be used to inflate the tire. Some molecules will remain in the cylinder. Right, the next one. When the bicycle is in use, atmospheric pressure, what do you mean by that? Atmospheric pressure? Yeah, that is also okay. That you can give that also as an answer. Anyway, it can't go, it will not go beyond below that. Agreed. Part B, when the bicycle is in use, the pressure is in the pressure in the tire falls. When the bicycle is in use, the pressure in the tire falls more slowly if nitrogen gas is used to fill the tires instead of air. That is a good thing of using nitrogen. It will be there in the tire for a longer period. Okay, and the bicycle, the pressure in the tire falls more slowly. Air is a mixture of mostly nitrogen and oxygen. Nitrogen molecules are larger than oxygen molecules. Nitrogen molecules are larger than the oxygen molecules. Suggests why the pressure in the tire falls more slowly with nitrogen gas. So they itself
It's
has
larger molecules, so it takes more time to move from place to place, right? Because it's heavier compared to oxygen molecule. Speed is less also.
So since it's larger molecule, it's not easy for them to escape comparing to smaller molecules. So they will take a longer time to escape the tire. So that means the tire will last longer compared to the regular air. Correct? So write the answer. Since nitrogen molecules are larger, nitrogen molecules are larger, it's harder for them to escape the tire. So it will take a longer time. For them to escape. Right. Okay.
So isn't it only 1 point, sir?
They're asking why it takes longer time, right? So I think that should be fine. Saying that it is a larger molecule, then it is difficult for them to escape. So it will take a longer time.
No.
Right, guys, write down the next topic. Nuclear decay, the topic. So there's a unit 5 consists of 4 topics: thermodynamics, nuclear decay, oxidations, and astrophysics and cosmology. So what we did is the first one, which is thermodynamics. So we are starting with the second, nuclear decay. Right. Right, and the subtopic under that. Different types of radiation. These are things that you have done for your O levels. It's okay. Quickly go through it again. There are 3 different types of radiations. There are 3 different types of radiation.
So is there like a main topic for this?
Nuclear decay. The topic is nuclear decay.
Okay.
There are three different types of radiations, full stop. They are alpha particles, beta particles, and gamma radiations. Okay. You have done this for local O-levels? Anyone else here from local O-levels? Who did local O-levels? You have done this for local O-levels? No? Okay, fine. Anyway. So these are the three types of radiation. And what are alpha particles? Alpha particles are, an alpha particle is a helium nucleus. Okay. A helium nucleus consists of what and what?
2 protons, 4 neutrons.
Protons and 2 neutrons. Correct. A helium nucleus. 2 protons and 2 neutrons. So that is an alpha particle. So an alpha particle is a particle which consists of 2 protons and 2 neutrons. Okay. So if you take the alpha particle, what is its charge? 2 plus 2, positive 2. 2 protons and 2 neutrons. Then what is the mass of the alpha particle in terms of atomic mass unit? 4. 2 protons, 2 neutrons. Proton has an atomic mass unit 1. Neutron has an atomic mass unit 1. Correct? So 4 nucleons. So which means it has a mass of 4. 4U. Correct? What is 1U? What is atomic mass unit? You do chemistry, right? Who doesn't do chemistry? 1, 2, 3, 4.
So is it 213?
Okay, according to the chemistry, you know what is the definition of atomic mass unit?
So atomic mass unit. I didn't hear you.
Yeah, what is the definition of atomic mass unit? What?
Number of protons and neutrons?
Atomic mass unit?
So has it got something to do with carbon 12
It is
atom?
mass of 1/12 of carbon 12, something.
Yeah, something like that. Yeah.
That's something like that, right? That is
Yes, something like that. Yeah.
am I doing the chemistry or not?
So we learned it in all also.
I learned this about 14 years ago. 15 years ago. So
So you have good memory, mashallah.
okay, so atomic mass unit is in kilograms, what is the value? 1.67 into 10⁻⁻27 kilograms. Yes, fine. Anyway, so if you take a alpha particle, it consists of 2 protons and 2 neutrons. So 4 nucleons. So its atomic mass unit, its mass will be 4U. 4 times the atomic mass unit. Correct? Right. Right under that, it's a subtopic, alpha particles. Alpha particles are helium nuclei. Alpha particles are helium nuclei. Full stop. They consist of 2 protons and 2 neutrons. They consist of 2 protons and 2 neutrons. So when a nucleus emits an alpha particle, its proton number decreases by 2. Its proton number decreases by 2. And nucleon number decreases by 4. Okay, so if a unstable nucleus emits an alpha particle, its proton number will decrease by 2, and the nucleon number will decrease by 4. Right on the next subtopic, beta particles. What are beta particles? What are beta particles? Electrons, fast moving electrons are beta particles, right? Beta particles are fast moving electrons. Beta particles are fast moving electrons. So when a beta particle is emitted from a nucleus, its proton number increases by 1. Its proton number increases by 1.
So can you go to the notes because I missed some points of writing from it. Yeah, thank you.
And nucleon number will remain unchanged. Nucleon number will remain unchanged. Okay, now listen. Now, a beta particle means a fast moving electron. So a beta radiation means a nucleus emitting a beta particle, and let's say becoming another nucleus. Now this radiation happens from the nucleus. Okay, from the nucleus, particle is emitted. But if you take a nucleus, originally, is there an electron in the nucleus? Are there electrons in the nucleus? No. There are no electrons in the nucleus. There are only protons and neutrons. So from how is a electron emitted from a nucleus? I heard it. Tell it. Yeah, a neutron splits into a proton and an electron, and that proton will remain in the nucleus. This electron is what emitted. Okay. So for an example, let's say if you take a nucleus, it has a proton number A and nucleon number B. Let's say it's emits a beta particle and becomes B. So the number of protons will increase by 1. Why? A neutron reduced to a proton. Okay. A neutron converts to a proton and an electron. So the number of protons will increase by 1. But the nucleon number will remain unchanged. What a nucleon number means? Number of protons
Protons plus neutrons.
protons plus neutrons. So number of neutrons is reducing by 1, number of protons is increasing by 1. So the total of protons and neutrons will remain unchanged. Correct? So in a beta decay, in a beta particle emission, and a beta minus emission, beta radiation happens. The nucleon number will remain unchanged. The proton number will increase by 1. Understood? Right under that.
So for the points you wrote until nuclear number will remain unchanged.
Yeah. And right below that. During a beta emission, a neutron converts into a proton and an electron. A neutron
How is the electron number conserved here?
during a beta emission, a neutron converts into a proton and an electron. Full stop. Proton will remain in the nucleus. Proton will remain in the nucleus. And the electron is emitted. Okay. Right on the next subtopic. Gamma radiation.
That's a,
Okay. Gamma radiation. Right under that. It is a high energetic electromagnetic radiation. It is a high energetic electromagnetic radiation with a high frequency. With a high frequency. Full stop. When gamma radiation is emitted from an unstable nucleus, when gamma radiation is emitted from an unstable nucleus, its proton number and nucleon number will remain unchanged. Its proton number and nucleon number will remain unchanged. Full stop. Its energy will decrease and it will become more stable. And it will become more stable. Okay. Right on the next subtopic.
1 second, go back, sir, please.
Ionization and penetrating strength of different radiations. Ionization and penetrating strength of different radiations. Again, this you have done for your O-levels. Correct. So if you take alpha particles, they have the highest ionization strength and the lowest penetrating ability. Okay. So if you take a beam of alpha particles and if you fire it through air, or if you, it can only move a few centimeters in the air. It will be ionized. So the ionization strength of alpha particles is extremely high compared to the other two. And its penetrating strength is very low compared to the other two. You can stop a beam of alpha particles even with a thick sheet of paper. It can't even penetrate through paper. Okay, right under that. Alpha particle, under that part A, alpha particles. They have the least penetrating strength. Least penetrating strength.
Everything is starting to flood into the brain, so when you keep, telling all these small examples and all.
You haven't done this folder?
No, it I have done, but like during COVID, then all stuff and everything, so forgot.
But now COVID is responsible for you forgetting it, no?
Yes, if COVID didn't come out, they've
Yeah.
been like,
Remembering.
first
right?
in the world or something.
Yeah, I know. Right. They have the least penetrating strength. They have the least penetrating strength and the highest ionization strength. Least penetrating strength and the highest ionization strength. Yes. What do you like to do the most on a Saturday morning? I see most of you people are carrying a very sad face, like someone has forced you to come and sit here. Why the hell am I doing this? Why do I care about the penetrating ability of alpha particles? Why are you giving a look like that? Who cares about penetration and ionization of alpha particles? Okay, what do you like to do on a Saturday morning? Tell me. Okay, be honest. What is the most interesting thing that you like to do in your life? Tell me.
Sleeping.
I mean, sleeping, is it?
Yes. Sleeping, gaming, watching.
Sleeping, put your hands up. Sleeping is the most interesting thing to do. The one person. Okay. Playing games. Okay. Watching movies. Okay.
So
Listening
you're
to music.
naming all the fun things, huh?
Huh? What you tell me? What is the most interesting thing you like to do? Football. Football. You? Playing cricket. You? Huh? Playing games. You? You? Taekwondo. You? Diving. You? Huh? Reading. Boring. You? Gym. Travel. Nothing. You? Boring? Going on. You? You? Coming late to class. Yeah. You? You? Nothing. You? You?
So when I had a ton of books, I used to love reading, sir.
Baking. You? Nothing. You? Dancing. Huh? So none of you like to study, is it? Okay, in your list, tell me. I know number one can't be studying. Okay, let's list it out to you. Where does studying stand? Second, third,
So is
fourth,
there negative points also?
third.
Is there negative points?
Huh?
Negative.
No, it's like this. Now you can't, yeah.
Where is your teaching stand?
Teaching stands, to be very honest, maybe like third. Yeah, I never expected it to be the number one. Obviously, it can't be, but it can't be way below. Okay,
So at the first.
for me, first is traveling, and then playing cricket, and then yes. Yeah. So my point is now you can't only do things what you like to do in your life. Okay, right? Now you all know Sangakar, right? So I heard once he's telling he loves playing cricket. Obviously, loves playing cricket. I have told you this, I think. But he hates going to the gym. Okay, but he can't play cricket if he doesn't go to gym. Simple, right? So if he wants to play cricket for longer, he has to be disciplined with the gym as well. So if you want to do things that you like to do, there will be things that you will have to do what you don't like to do. So that is life. You can't only do what you like to do. If you only do what you like to do, also it will get boring after a point. You will get bored. Just imagine you like to eat. 24/7 you keep eating. Won't you get bored? You like to play football. But if you play 24/7 football, it will get bored. So you need the right balance. So studying also somehow has to squeeze in and you have to balance it, whether you like it or not. Okay? Fine. Don't give a sad face on a Saturday morning. Just be a bit energetic. Fine. Guys, part B. Gamma radiation. Gamma radiation. So they have the highest penetrating strength. They have the highest penetrating strength. At the least ionization strength. And the least ionization strength. Okay. So guys, gamma radiation is very powerful. Obviously, the electromagnetic radiation with the highest frequency. So it's very energetic, very powerful, highly penetrating. So it can almost pass through anything. So if you are to block a beam of gamma radiation, you need a thick lead sheet or thick concrete is needed. Okay. So there is a reason if you take these power plants, nuclear, mostly they are made of huge concrete, they have huge concrete covers to make sure the gamma
Concrete
radiation
and
is,
lead also, right, sir?
sorry?
Yeah, is lead also there?
No, it's mostly concrete is what used. Practically concrete is what used, but yes, a thick sheet of
Yeah.
lead used to
Because
stop.
it's cheap and everything.
Yeah. Part C, beta particles. Beta particles. Okay, so guys, beta particles have a penetrating strength more than alpha, but less than gamma. Same with ionization strength. They have an ionization strength more than gamma, less than alpha. Okay, right? penetrating strength of beta particles is higher than alpha particles. And lesser than gamma radiation. Okay. And below that, ionization strength of beta particles is ionization strength of beta particles is higher than gamma radiation, and lesser than alpha particles. Lesser than alpha particles. Okay. Right. Alpha particles. Fine, you can take a small break. See you in 15 minutes.
Thanks, sir.
I was reversing fluid mechanics, sir. How do you answer
Hello. Right. Let's write on the next subtopic. Rate of radioactive decay. Rate of radioactive decay. Right under that. Radioactive decay. Radioactive decay. Radioactive decay is a spontaneous and random process. So any radioactive nuclide may decay at any moment. So any radioactive nuclide may decay at any moment. Full stop. The probability of decay per second. The probability of decay per second probability of decay per second is known as the decay constant. Is known as the decay constant within brackets lambda. Lambda. Right below that. The number of nuclei decaying per second is known as the number of nuclei decaying per second is known as the activity is known as the activity within brackets A of a radioactive sample. Of a radioactive sample. Okay. Any radioactive nuclide may decay at any moment. Right? What is lambda? What is lambda? Decay constant. What is A? Activity. What is activity? What is activity? The number of nuclei decaying per second. Okay. What is lambda? Decay constant. What is decay constant? The probability of a nuclei decaying per second. That is lambda. Okay. Right. So guys, the equation which connects A and lambda is A equals minus lambda n. So which means n is the A is the activity, A is the decay constant, and n is the number of undecayed nuclei in the sample. Number of undecayed nuclei in the sample.
So won't we get confused with the wavelength and decay constant for the lambda?
Not really, because in this questions, you are not going to meet anything. It's wavelength. So there will be only one lambda which is used here, which is the decay constant. Right? A is activity, B is decay constant, sorry, lambda is decay constant. N is number of undecayed nuclei in the sample. Okay. The unit of activity is what? BQ, which is becquerels. Becquerels. The activity is measured in becquerels. Why? What's funny about it?
Yes.
Becquerels. Right? Fine. Then write down a question. BEQ, UR, I'm not really sure. RRELS, I guess. But I know BEQ, becquerel. Okay. Right. The decay constant for carbon.
Sir, can you, so what's the SI unit, sir?
It's not an SI unit. Becquerel, BQ. If you want, we can derive an SI unit.
No, what do you write before BQ? Is it unit? You write unit
Yeah.
or width? Looks like width.
Activities unit is becquerel. Unit of activity is becquerel. BQ. Right. The decay constant for carbon 14 is lambda equals 3.84 into 10 to the power minus 12 per second. The decay constant for carbon 14 is lambda equals 3.84 into 10 to the power minus 12 per second. Full stop. What is the activity of a sample of? What is the activity of a sample of? 100 billion atoms of carbon 14. $100 billion atoms of carbon 14. Okay. So to find the activity, A equals, we can use A equals lambda in. So the lambda is 3.84 into 10 to the power minus 12 into the n is 100 billion, which is 100 into 10 to the power 9. That will be how much? Minus sign is not necessary because we are looking at the value of the activity now. The minus sign is just to indicate that the number of, during this decay, the number of n is reducing, right? When decay happens, n reduces. So that minus sign is to signify that. So when you ask for the activity, minus sign is not important, just the value is what needed for that instance. Okay. Which is 0.384 becquerels. Right. Right on the next subtopic. Fluctuation of the number of undecayed nuclei in a sample. Fluctuation of the number of undecayed nuclei in a sample. Okay. So guys, if you take a sample, let's say,
Sir,
yeah,
can you show me previous questions, please? Thank you. Yeah. Thanks.
Right. Whereas if you take a sample, right, the number of undecayed nuclei in the sample, let's say at the beginning it has n naught number of undecayed nuclei. So with time, the number of undecayed nuclei in the sample will keep on reducing while it's decaying. So it will have an exponential decay curve. Okay. And the equation is given by the number of undecayed nuclei in the sample is given by n equals n naught e to the power minus lambda t. Okay, an exponential decay equation where n naught is the initial number of at the beginning the number of undecayed nuclei, lambda is the regular lambda, and t is the time. What is lambda? Decay constant. So this capital N will be the number of undecayed nuclei remaining in the sample after time t. Take down the graph and write down the equation.
Excuse me, sir. In your notes, you wrote A is equal to minus lambda n, sir.
Yeah, in the calculation that we did, the activity value is what required. So you just take the magnitude of it. That minus sign is to indicate that the number of nuclei is reducing.
Okay. So when do we use the minus? Do we ever use it like in
Not really.
when writing that's or not? Okay.
I didn't get you. Come again. It's an exponential decay. An exponential graph will have the x-axis as the asymptote. Now, for an example, let's say if you take a number and if you keep on making it half, it becomes smaller and smaller and smaller and smaller and smaller. It never reaches zero. So that is an exponential decay. Right. So the equation is n equals n naught e to the power minus lambda t. And define the terms. N is the number of undecayed nuclei in a sample at time t. And n naught is the number of undecayed nuclei in the sample at t equals 0. Okay. And lambda is the decay constant. Right. So now look at this. N equals n naught e to the power minus lambda t. Then we can come up with this hold on. There's any did we meet log before this in the syllabus? Yes, right. So I have told you if n equals n naught e to the power minus lambda t, and if I take ln on either sides, then we can write it as ln n equals. If I take ln on either sides, I can write it as ln n equals ln n naught into e to the power minus lambda t. Correct? Original equation is n equals n naught e to the power minus lambda t. So if I take ln means log to the base e. on either sides, ln n equals ln n naught e to the power minus lambda t. So which is ln n equals, if we use the product rule of logarithms on the right hand side, ln n naught into e to the power minus lambda t will become ln n naught plus ln e to the power minus lambda t. Correct? Which is ln n equals ln n naught. ln e to the power minus lambda t is equal to minus lambda t. Agree? Do you understand this? So this is another form of the same equation in the logarithmic form. ln n equals ln n naught minus lambda t. You can use this as well. Okay, take it down. How many of you do maths? Okay. Okay, right. There's now, I can simplify this a bit more. Look at this. If I take this minus lambda t to the left, it will become lambda t equals ln n naught minus ln n. We can use this, okay, no harm. So if I take the minus lambda t to the left, it will be lambda t equals ln n naught minus ln n. ln n naught minus ln n, I can write it as ln n naught divided by n. Okay. So this is another one. ln n naught over n equals lambda t. Take it out. Okay, right. Now, write down the right below that separated. The activity of a sample also has a similar variation. The activity of a sample also has a similar variation. And take down this equation: a equals a naught e to the power minus lambda t. So where a is the activity when the time is t, a naught is the initial activity at t equals 0, and lambda is once again the decay constant. Okay. So you can do the same thing here with logarithms. If I take ln on either sides, okay, you will get this one. Ln a equals ln a naught into e to the power minus lambda t, which is ln a naught plus e to the power minus lambda t. So which means ln a equals ln a naught minus lambda t. Take it up. No, just take it down for now as a different equation. There are certain questions where the ln form will be helpful. Take it down. When you do examples, you will get it. Okay, right. Right in the question. If the seller in a house in Noah's, okay, just take, if the seller in a house contains 6.5 billion atoms of 6.5 billion atoms of radon 222 gas, with a decay constant of 2.1 into 10 to the power minus 6.
So could you please decrease the size so you can see it clearly?
With a decay constant of 2.1 into 10 to the power minus 6 per second. How many radon gas atoms would be there 1 day later? So N naught is 6.5 billion atoms, 6.5 into 10 to the power 9 atoms. Decay constant is 2.1 into 10 to the power minus 6 per second. How many gas of atoms would be there after 1 day? So after 1 day means 24 hours into 3,600 seconds. 24 into 3,600 is 86,400 seconds. Okay, so you use the equation N equals N naught e to the power minus lambda t. N naught is 6.5 into 10 to the power 9 into e to the power minus lambda is 2.1 into 10 to the power minus 6 into t is 86,400. Which is 5.52 billion. 5.42. Yeah, 5.42.
So we are supposed to remember which this one is E, because they won't even let us keep our calculator covers.
What I didn't get you. Tell again.
No, we have to remember how to get E in the calculator, because they don't allow us to keep the calculator also. Calculator cover.
What is it again?
The letter E is in the calculator.
Yeah.
You have to know how to get it right. So you have to remember that also.
What is there to know about? How to get E on the
How do you
calculator?
get the letter? I forgot. Yeah, I forgot the function. How to get E, the letter E in the calculator? How?
It's there. It's written here. E to the power is there on top of the LN button.
Where?
On top.
Ah, okay. Sorry. Forgive me, sir. Forgive me. I'm a human.
Right. Okay. Fine. No, we'll continue from here on the next day. That's it for the day. See you next week. Bye, people. Take care.
So homework, sir?
No, still you can't do any questions.
Okay, sir.
You will get.
Thanks.
That's here. Welcome back. That's here. Welcome. Welcome.
Thank you, sir.
Welcome back. See you. Are you new to class? When? Today. Here. From which school are you? Alright. You're from which school? Have you done unit? You left school. What is your name? You? So you have done your master. Okay. Do you understand what you did today? Yes. Thermodynamics. This you understand. Syllabus we are done. Unit 4 we are fully done. Unit 5 also. Out of the 4 now we have done one topic. So somehow you have to catch it up. Okay. Right. Hi. Are you new to class? What is your name? Hansa. From which school?